All right, so in this video, we're going to look at examining a little bit more with periodic relationships that we started discussing in our breathing activity in class the other day. So when we went through the activity, we discovered that a periodic relationship between two variables occurs when our outputs demonstrate a repeating pattern over successive equal length input intervals. So basically, as our x values increase, we can see a pattern in our outputs that continues to repeat itself over and over again. And we define the period as the length of time that it takes to complete one full cycle. So if I'm looking at this graph, I would say that, let's say that I choose that as my starting point. I would trace the graph until I get back to a repeating pattern where I'm back down to a minimum that goes and creates that same shape after it. So this right here on my graph would be what I would consider one full period. So if they want to figure out what is the least possible period for that graph G, well, I would just say, all right, well, I started at 1, I ended a cycle at 6, so from 1 to 6, that's 5 units, or you could actually subtract your values and say 6 minus 1 is 5, and so that would be the length of one period there. Now, if I want to, and this is where we kind of left off on the breathing activity, once I establish the period, even though the graph stops at 9, I know that this pattern is going to continue over and over as my x values get really, really large. So all I have to do when I'm trying to predict values that don't appear on my graph is think about where in the next period, or after I take away full cycles, where in the next period would I land. So we know that this has a period of 5, so every 5 units it's going to repeat itself. So if I'm looking at G of 14, well, I know that in there I'm going to complete 2 full cycles because 2 times 5 is 10. So I'm going to have 2 full cycles plus that extra 4. So then in the pattern, if I take away those 2 full cycles, then I start repeating myself 4. So this is going to have the same output value as G of 4. And I can look at my graph here and say, oh, G of 4, I'm at 7, so that would be my value. Now, if you're not quite certain how many, you could always just grab your calculator and divide it out. And you can say, all right, well, I'm not quite sure how many full periods I would get through in 72, but I could divide 72 by 5 and realize that that goes in 14 times, and then there's a decimal. So it's going to go in 14, and that gives me a remainder of 2, because 14 times 5 is 70. So that means G of 72, I can break it up into 70, which would be 14 full cycles, and then I would be starting again an extra 2 past that. So again, if I take out those full cycles, that's going to bring me to G of 2, and on my graph, G of 2 is just 6. Now, we could even work these backwards. So if I give you a negative, what I can do is figure out, all right, well, how many full cycles will it take to get me into the positives? So I can keep adding 5, adding 5, adding 5 until I finally get into that positives. So if I look at this one right here, I can say, all right, well, if I add 4 full cycles, I'd be adding 20 units to my graph. And so now G of negative 17 is going to have the exact same effect as G of 3, because negative 17 plus 20 would be 3. And if I go on here, G of 3 lines up with 7. So instead of having to keep drawing out the graph, we just figure out, all right, starting from 0, how many full cycles would I get to each of these values? Once you establish your period, figure out how many full cycles do you get, and then whatever is left beyond that, that's where you're starting back at 0 and you're going there. So, you know, G of 14, again, 2 full cycles of 5 plus an extra 4. So then that would be G of 4. And then I can just grab that off my graph. G of 72, I can do 14 full cycles. That would take me 70 units. That's going to wrap me back to have an extra 2 again, so that would be the same as G of 2. And then again, if I'm at negatives, I can just keep adding on cycles until I get into the window of my graph that I see. It gets a little bit trickier with tables, We're limited now to only the values that we see in the table, so we have to hope that whatever they're asking me to evaluate, once I know what the period is, I can manipulate those values to produce one of those outputs there. So h of -2, well darn it, I don't have a -2 input. But they did tell me, luckily, that this has a period of 5. So I know that every 5 units, this is going to repeat. So if I add 5 to all of these numbers, these are going to be the outputs. If I subtract 5 to all of those values, those are going to be the outputs. And if I keep repeating those multiples of pi, I'll keep getting those values. So I'm going to use the same strategy I did up here, but I just have to keep working and hope that I'm getting an input value that occurs on that table. So for h of -2, again, not on my table, I can start, well, if I add a full period, -2 plus 5, that's going to give me 3. I'm going to cross my fingers and hope that I can evaluate h of 3. And luckily we can, because at 3 on my table, I do have a corresponding output of 0. All right, so again, I can add or subtract if I need to. For h of 6, 6 is again not on my table of values, and I know that if I add 5, that's not going to help me because my values stop at 7. So we can, again, work it backwards. h of 6 means I've gone past a full period, so let's rewind and take a period away, and that would leave me h of 1. And again, luckily, h of 1 is one of my values on my chart, so h of 1 is -2, so I know the value for this guy. All right, and then we can even bring back in compositions like we were talking about before. We just have to work again, just like a regular composition, from the inside out. So first thing we would do is try to figure out, well, what is h of 9? Now normally we just go on the table and be like, hey, there's 9, and we grab it. Again, 9's not on my table, so I'm going to have to rewind some periods and hope up for the best. So again, if I want to go onto the table, I need to go backwards. So I'm going to subtract a period. So h of 9 is going to be the same as h of 4. And we're lucky. h of 4 is on our table. h of 4 is 3. So h of 9 is the same as h of 4, which is 3. So now if I want to finish this composition, now I can replace h of 9 with that value of 3. And good news, h of 3, it's on my table. That equals 0. So we are finished with that problem. So anytime we have periodic behavior, once we establish our period, we can then add single periods. We can add single values of 5 or subtract single values of 5. Or sometimes we might have to add multiples. Again, that's what we had to do up in that example up there. Okay? So when we are looking at periodic behavior, sometimes it's helpful to see that there is some notation that's going to describe what's happening in there. So in our last example, we saw that the period of h was 5. So that meant that every time we took our value, if I were to shift this table 5 units to the right or 5 units to the left, those translations would produce those same output values. Same thing here. This guy had a period of 5. I could add 5 to the right, and it's going to keep repeating that pattern. So all of our periodic functions are translations on top of themselves. They shift left or right based off of that period length and multiples of that period length. So if I want to then say, all right, well, here's a graph that shows me some periodic behavior. We see 2 full periods. You can see there's one of those like weird V shapes, and then it repeats itself again. So those would be 2 full periods. And if I want to find all of the input values that are going to yield an output value of 1, I'm not just going to say, well, here we go, there's one value that does that. I want you to create a rule that will generate all of them. So we're going to take that idea of transformations and translations and think about that. So if I want to find where it's going to give me an output value of 1, I'm looking where my y value is 1. And I can see right now that that's happening at 2, and then later on it happens at 6. And that makes sense because our period is 1, 2, 3, 4 units long. And so every 4 units, this little check mark guy is going to come back down to that height of 1 and then go away and then come back down. So we're going to start with this point right here. We're going to say, all right, well, the first one occurs at x equals 2. Well, then all of my x values that are going to have that are going to be 2 plus or minus. Again, we can go forward or backwards. My period, and then however many intervals that we do that. So let's say we use p for period. We can say, well, that's 2 plus or minus 4p, where p represents some type of integer. Or we can even say a whole number, since we did plus or minus. If we did just 2 plus 4p, then we could say integer, and that would take care of positives and negatives. So now this is saying, all right, it's going to be 2 plus every multiple of 4. If I do 4 times 1, that would be 2 plus 4. If I do 4 times 2, that would be 2 plus 4 again, and that would bring me over here to 10, which we haven't quite made it there on that graph, but we can see that that's where that guy was going to be heading anyway. So when we're working with periodic phenomena, we're just basically trying to find our values where the cycle repeats itself, and we can just add or subtract multiples of the period once we figure out what it is, and then use a graph or a table to find our outputs. All right, so for the rest of class today, you're going to try to practice with this idea of periodic behavior, and we're going to then see how this connects to other periodic phenomena that we're going to study throughout the rest of this course.